We will now analyze the motion of a particle moving around a circle at a constant speed. The punchline is that even though the speed is constant, the acceleration is non-zero. This is because if I look at the velocity at different times, it will be pointing in different directions. So the velocity is changing and the acceleration is non-zero. The end result for analysis is that the acceleration is related to the speed at which you're moving around the circle and to the radius of the circle. The acceleration is the square of the velocity divided by the radius. And you can verify this has the correct units. So if I am moving faster, the acceleration is larger. If the radius is smaller, the acceleration is larger. And this acceleration always points directly to the center of the circle. We'll proceed by analyzing the motion diagram for exactly this setting. So the rest of this video will be deriving this result. I'm going to analyze the motion diagram for an object moving in a circular path at a constant speed. We call that uniform circular motion. I'm going to take the origin to be at the center of this circle. And I could draw radii vectors corresponding to the distance to each of these points. For simplicity, to make it easier to read, let me change the colors of those. I can also draw the displacement vectors, which, as we know from before, are simply related to the velocity. So this vector here corresponds to the average velocity during this interval times delta t. Now we can simply create the velocity vector for the next time interval. And then finally, the next thing we know how to do is how to combine two subsequent velocity vectors to get an acceleration vector. Okay, so we take the difference between two subsequent position vectors. That gives me a velocity vector times delta t. We take the difference between two subsequent velocity vectors times delta t, and that gives me an acceleration vector times delta t squared. Now I'm going to show you some magic. If I look at this angle up here and compare it with that angle down there, those angles should be the same. The argument is that the relationship between this vector and this vector, this angle here, is the same as that angle there. And if you add up the angles in a triangle versus adding up the angles in a line. But intuitively that should make sense. This angle is equal to this angle. Well, that means that this triangle down here is similar to this triangle here, right? Which means they have the same angles. It's just they're scaled relative to one another. That means if I take the ratios of the lengths of sides of these two triangles, they should be equal. So if I take the length of one of these long sides there, well, that's nothing but just the radius of this circle. And then if I take the length of that side there, that is nothing but the speed times delta t. Well, that should be the same as taking the ratio of this length and this length. So this should equal, all right, again, that is just, this side here is just the speed, delta t, and this length here, that is the magnitude of the acceleration times delta t squared. Well, miraculously, the delta t's all cancel. And we're left with a simple expression. Usually written as a equals v squared over r. So the magnitude of the acceleration for uniform circular motion is simply the square of the velocity, or the square of the speed, divided by the radius of the circle. All right, let's think about this for a second. All right, so first, it's dimensionally correct. The dimensions of A are meters per second squared. The dimensions of V are meters per second. And the dimensions of R are meters. And so these two sides have the same units. The next thing to note is that if I make the radius smaller, then the acceleration is larger. Well, that makes sense. The acceleration is the rate of change of the velocity. The velocity vector is changing more rapidly, even if you're moving at the same speed, if you're on a tighter circle. There's more each time unit to time unit, there's a larger change in that vector. And then finally, the acceleration is larger if the velocity is larger. That also makes sense, because the faster you're moving, the more rapidly that velocity vector is changing. And then one final thing is the direction. Take this vector here and move it over there. It's pointing right to the center of the circle. Right? And this we know that if you have motion with constant speed, then the acceleration vector has to be perpendicular to the velocity.